Okay, let's go ahead and get started. See, actually, during the pre-show, the chat actually getting a little bit of attention. Tell me if my audio levels are a little bit off, or something. I can never tell with these guys. Today, we're going to be doing something a little bit different. Thanks, Super Ray. I'm not having a little bit of trouble seeing where everyone's coming from. I recognize Razor from Sega Extreme. I don't know, Super Ray, where you came from. You have a different username on it. Oh, there he is. Okay, so what's on docket for today? What I'm going to try doing is I'm going to try running a quantum mechanics simulator on the Sega Saturn. So it's actually not that bad. It's the math for it, for the stuff that I'm planning on doing today, is relatively straightforward if you've ever taken a calculus. We're going to try and visualize and talk through what's actually going on, and this, the kind of stuff that I'm implementing here is a simplified version of what I actually use in my real job, where I simulate these quantum mechanical systems, so-called one-dimensional systems. I'll go more into detail about what it means to be a certain dimension when you're talking about a system. But for now, basically, we're just going to be plotting stuff. So to start out with, we need to figure out how to plot something on Sega Saturn. So, okay, we could do the matrix method, and that maybe I could figure out a way to get that to work well on the Saturn. However, Huygens Fresnel, who is that? Huygens Fresnel. I know those two scientists. I don't know who's using their names. But anyway. Oh, there you are, Pedro. Okay. So, Dr. Pedro over there, he's an actual physicist. He outranks me a little bit. He's got a couple more years of experience on me. Okay, let me crank down the volume. Tweaking these. So I actually, as opposed to the normal Saturn retro gaming and homebrew scene that I normally invite to these streams, I've invited a handful of physicists I know in real life to maybe provide a little bit of commentary in case I'm not doing a good job of explaining. But they're also probably going to troll me a little bit with some references to things I probably don't need to be trying to do on the Saturn. Anyway, so moving on. We're going to try to do a basic plotting software. And luckily, Johannes already gave us a pretty good head start with his paint program. So let's go ahead and try to run that. So already we have some... I mean, it's a relatively straightforward, like 80-line piece of code that can draw lines. And instead of using user input to do that, we can just ask that it does it in terms of a mathematical equation. Now, we should be at 224 by 320 by 224. So let's try simulating 320 x values and trying to support... Oh, we actually see the... screen coordinates down there. Okay, yeah. So I guess it's more like 319, I guess, or something like that. I don't know. I don't know where it cuts me off. But we're going to use 320 or so x values as the boundaries, and then I guess we can try to vary it between 0 and 1, whatever our unit is, our energy unit. I'll get into with the actual math of that later. Right now, we just want to be able to plot something. So, okay, let's... Okay, I will be developing through the emulator, but then I will be moving it onto the Sadiator once it's actually ready to run. Because otherwise, I'm going to keep going back and forth on SD cards. It's going to take forever. Okay, yeah, exactly what Shane just said. So we have to do a little bit of dev first before we start doing live tests. But it will be running on the Saturn before we're done. Okay, so what do we have here? We have Joe's code for this. I don't plan on using the cursor sprite I'm going to have the program do the drawing for me. So, sorry. We do not need the cursor sprite here. We don't want to load up the cursor sprite. Let's keep that code in there just in case. I'll keep the gamepad code. We do not need that. Where is my draw? Okay, we've already commented that. So if we're not loading up the code, hopefully, did I just break it by doing that? Yeah, that's what I was asking about earlier. In I think it was in the Saturn dev channel on Sega Extreme. Was that you? No, it was. I can't pronounce his name. Something starts with an I. Talking about. There we go. Cursor's gone, but I can still draw. That's good. That's all the code I need. So what I needed was a dev cart where I can instantly go in through USB. I know the Sadiator technically has that ability, but the firmware is not there for it yet. And I think Professor Abrasive is busy doing handful of pixels. Oh, that's unfortunate. Let's back. Okay, let me try that again. Compilation. I don't want to block chat if... Oh, I see what's going on. Here's a quick and easy. Drag this chat log. There we go. It's always fun when we're doing live stream. Edit. There we go. A little bit better. I can try to... There we go. Now that looks... Okay, that's gonna have to do. That there. Now here's the thing, if I shifted 8 pixels to the left, I'm going to be cutting off pixels that I want to be able to see. So I'm just going to shrink it a tiny bit. So yeah, the dev cart by Cafe Alpha is open source. The only problem with that is I'd have to actually make my own hardware, and I'm not too confident in trying to get that board printed and custom made run, and putting it in my only Saturn and having it break something because I crossed the stream where the 5-volt source or something like that's going. Anyway, let's do... Here's the thing. I'm going to have to use floats. So, first off, what's my DX? I want... No. That was a PlayStation. I got a PSIO, and that's what you helped me solder together. So the PlayStation 1, or the PSX, or whatever you want to call it, the PSIO requires a board modification, and Wiggins Fresnel over here helped me patch up a bad trace job that I did. A lot of effort on his part, but now I've got a PlayStation that can play anything. Okay, what was I doing? I'm doing, width? Okay, let's do float width. Well, first off, animator is equal to 1e minus 9. This is going to be kind of like hacky until I, Oh, dude. Seriously, between me botching up the job and having Pedro fix it up for me and me having to order parts from Australia, it took me like a year and a half to get my PSIO up and running. It was an experience. Yeah. Okay, so I'm hacking together a lot of the stuff I'm normally going to use, and then I'll kind of move stuff over into the places they need to be. as I go along. So float width is equal to let's do 10 nanometer well. There's nanometer. Presumably there's a way to do that. I just couldn't figure it out. Maybe you have to actually burn the disk or something. Width divided by 320 units. There we go. Actually, for now, let's just do 1 unit at a time. So we'll do a width of 320. I did put F at the end of these guys. Probably. So we're gonna define our x-axis. This is gonna be, let's do a for loop. For I equals 0, I less than 320, I plus plus. Yeah, I've been having the same trouble too, so that's why I got the PSIO, so I don't even try with the PS2 anymore. In fact, most of the time when I use the free McBoot to boot up PS2 games, there's always some weird error that I have to figure out a way around. Like, I can't play Guitar Hero properly unless I have the disc. Okay. So we want our x values. Oh, we actually should probably define our x first. So we're going to do an array of floats. You know, it's been a little bit since I've actually went back and touched C, so I'm probably making some stupid mistakes here somewhere. It's like, what, 20 or 30 or $40 for the network card, and then you just slap in an old ancient hard drive in there. Xi is equal to I times dx. Seems reasonable. Going from 0 to 320, right? Yeah, that looks about right. Barring floating point errors. Okay. And then let's also make our y values here. So yi is going to be what? Xi. Let's make a quadratic curve centered at we centering at. We're going to center at let's center it at, I guess halfway through is what, 1600? 160, sorry. Well, we have a different mod for the Dreamcast. I have the USB GD-ROM, and you have a aftermarket GDEMU. So I technically have slightly more support than you do in terms of compatibility for certain games. Okay, great. I won't tell them about that part. Okay, granted, I paid money for the quality. Let's move these declarations up out here so that so that I can use them in the draw command. So we're going to put a pixel in the background. So this is a built-in Joe command that I can now use. What I need to do is I need to round the floating point down to are we doing our callbacks on? We got gamepad and my draw. Let's put the callback on my draw. This part anymore. I don't need these guys either. I'll leave one Joe print just in case I want to copy it over. Graphic. There we go. Oh yeah, you got a pretty nice Plex server going on there, and I've been abusing it probably, trying to use it on the web interface. Okay, so we want to put the pixel onto the location defined by Y. Okay, and Y is going to be set up ahead of time in Jomain before we start doing our callbacks and drawings. I don't know if we want to blank the background. Is there... Well, we'll look up if we have to blank the background later. For now... Pixel and background. Joe color blue. Blue's good enough. But I do want... let's do Joe color white. On a black background. For that. I think it's a little bit easier on the eyes to see... white on black as opposed to black on white text and stuff. Okay, so real quick, does anyone remember how we round floats down to ints very quickly without having to worry too much about it? Z round float to int. Oh, I don't mind a cast, I guess. If I do a direct cast, will it work? Okay, probably will. Okay, let's try that. So we're gonna do a direct cast. So we have angle. Oh, whoops! I'm editing the wrong thing. So let's repeat that for loop that goes over all 320 values. All right. But now we're gonna do our x value as cast our int down to x, or cast our x down to an int. Sorry. Same thing with our y, and we're gonna do it in white. And these guys don't need to be here. Is there a blanking? Okay, clear background. There we go. We're gonna do that. We're just gonna do a normal, like, just like a V blank, I guess, or however you want to call it. Or not a V blank. V blank is more of a timing thing, but green blank. Let's see if this worked. Of course it did. Joe color blank. Whoops. Did I make that same mistake down here? Nope. Shouldn't have. Alright, let's see what's going on here. Line 85. You knew we weren't going to get away with this. Oh. Well, can't forget our semicolons. If that was it. Yeah, that looks like that was it. Just a stupid semicolon. Always something. Oh no. My blanking function is a little bit too strong. Okay. We'll solve that problem when we get to it. Instead of clear background being done on the draw command, we'll just do it manually. With the start button. We don't need to draw circles. I'll keep the underline in red command with A button. I don't feel like I'm gonna want to use cursor. Actually, yeah, if I'm not going to use the cursor, I'm just going to get rid of all the crap. There we go. That, come on. Oh, you're good for it. Will it though? I mean, it's how many floating point operations are we doing here? That many. Oh crap. I feel like we should be okay, let's well, how would you do it then? Because yeah, put pixels slow. I'm doing the naive way, just try and get it done. So let me see. Maybe let's go back to black on white just in case I'm missing something. In this case, let's only draw like the center few pixels. Like 150 to 170. What do you mean outside border? Oh, you know what? I'm not screening for values that are above and below the boundary. I might be breaking the engine doing. Okay, it says graphing. It's not graphing, but it says it is. It should be graphing based off of Joe Color Black. Okay, let's try seeing what happens at %D, %D, and we're gonna see what happens when I cast down. Oh, that was the incorrupt thing to write. Okay, should have caught that. But while we're here, let's see what the values actually look like near 160. Expect them to be 0 or near. Yeah, that was a silly mistake. Like I said, I'm a little bit rusty. We'll pick up speed as we go along, because it's going to get interesting once I actually get to the physics of it. Oh, there we go. I mean, I preferred something a little bit more continuous, but you know, it works. So for now, let's try. Let's go back and switch our colors back. I want that. I mean, kinda. Yeah, kinda. That's fair. I feel like the Saturn should have a little bit more power than the TI-83, but I can't say that for certain. I'm definitely not using the power of the Saturn intelligently right now. First off, we shouldn't be using floats, but that's the only way I can think of handling orders of magnitude we're going to need. Come on. Okay, so let's swap the color real quick. So what I'm worried is that, where's my white pixels? Okay, Joe printf color is white. Pixel and background is... Oh, that's... You know what? Let's get rid of that. Okay, that just confused me. White. And let's continue this on to about 180 or so. Here's the thing, if it's got built-in Wi-Fi, I think it needs to be powered the whole time. And that means I basically have to keep the Saturn on, and then in order to actually do anything with it, I have to restart the Saturn anyway. I'd rather wait until either I get a dev cart or Professor Abrasive does something to add that functionality, because there's a USB port on the Sadator. It should be technically capable of doing that. Okay. I get the feeling that I'm allowed to draw off boundary and it's just going to ignore it. So let's try that. Oh, I know what I can do with cursor position. I can do cursor position is my index, and then I'll just do cursor position X. Oh, and this is gonna be fun. If cursor position X is equal to I, then I get to draw this thing in red. That'll be neat. Else, draw it in white. That way we can highlight the thing that we're looking at, and it'll also show up as a thing that we're doing. The CD editor basically tries to act as much like a real CD as possible. So you can do the soft reset with the ABC start command, but it doesn't have anything special that takes it back to its own menu. Right now you just kind of turn it off and on again, manually. I don't know if that's going to change in the full release. I don't think it's high on the Professor Brace's priorities right now. Right now there's like a handful of games, like maybe 5 or so, that won't boot on the CD editor, and those are like, because we've completed the entire redump test set. So we've tested all the discs available for official release on the Saturn, including the Japanese, the European, etc., etc. So he's fixing the boot issues on the last few games, doing multi-disc support so we can play things like Deep Fear, and then we'll get around to adding nice features like that, and I guess my USB dev cart in. Okay, so I kind of wish I didn't turn away that. I could have just commented it out. Okay, let's try Joe Engine. Let's go to Joe Engine and look up the documentation for. Come on. Go. Where's my controller? For content. Keep his controller stuff. Yet. Input? I bet it's input. There we go. There's input. So what I want is key press down for right or left. That's what I'm looking for. If so, pressed is distinct from being held down, and distinct from key up. I think pressed is just it'll trigger once when you press it down, but it won't repeat even though you hold it. Is what I want. There we go. And I'll do cursor position. Equal or cursor position plus plus, and do an additional if cursor position is greater than or equal to 320. I'm going to do cursor position is equal to cursor position minus 320. And then we'll do something similar for left key. Or if it's less than 0, add 320 to it. Minus minus as well. Seriously? Too few arguments. Oh, did I use... Oh, I think I need Joe pad 1 depressed. So, because of the ongoing pandemic, it's hard to say when the Sadiators actually become available, because he is going to have kind of this production setup. He's already talked to companies about it. So, at some point, when things stop getting all crazy, they will be able to be produced in bulk there shouldn't be too many supply issues, from what I understand. This isn't his first rodeo. He's released other pieces of hardware. I think the famous one he's done is like the Dragon Derp or whatever it's called. Oh my, did I break it? I broke it. Oh, I broke it. Okay. Let's go back to plotting on the reduced range and see if that thing that I did actually works. So cursor position 160. I think he said that from what I understand, it's probably going to be a more expensive option compared to Ren Mirror and stuff like that. Because he's got some form of protection on his IP, and he's got... Oh, okay. Okay, it's not doing the behavior I wanted, but... So why did it break last time? This is running smoothly. So as far as I can tell, it's going to be one of the pricier options, but it should be just plug and play, easy to use, work well. I don't know if he's going to change anything about that. Once again, it's not my product, so I don't know exactly what's going on with it. I just help test it out. I have conversations with him, but he just works on it, and then we find out when there's like a firmware update. There we go. That's what I want. So down is when you just press it down. Now, why wasn't it working before? Maybe I need to put in a check to make sure that it's not drawing off screen. So I think... Okay, first off, I need to do 224 minus whatever that is to get the right orientation. Because the coordinates on the screen start from 0, 0 at the top left corner and go down and to the right in increasing value. That's not what I want to display. So it's flipped upside down, basically. Second thing is... I need to take this value over here and wrap this conditional around everything to make sure that I'm only displaying stuff that will actually appear on screen. Whoops. Jury rig our plotting, Acme plotting software. So this is greater than or equal to 0, and this is less than 24. Now, I'm going to be less afraid of going from 0 to whatever value. That might slow things down, but I'm open to it. Okay, this seemed to work. So I probably was stressing out the drawing function by giving it values it wasn't prepared for. It's just too big. Let's go ahead and dampen this quadratic curve a little bit. Let's just divide it by like 100 f. And then let's go ahead and try that idea. I will... If let's do it first so we don't overwrite that red dot that I want. If I greater than 1. So Joe would draw a background line. Let's look that up. Draw background line. There we go. Give our x and our y coordinate and our new x and our y coordinate. Okay, that's basically what I expected. Okay. So, do background draw line. We're gonna have our old coordinate, which is this, with previous index, -1, -1, new index, I, and then the color is, I guess, just gonna be white for now. Oh, you're right. It doesn't check off screen. I probably just crashed this thing. Oops. The heck is that? Huh. Okay. First off, let's put this thing back inside the. It might just be an off-screen error, where it breaks in a different way than the pixel in background. There we go. Oh, let's also check that the previous Y was on screen. One. So we're only going to be drawing stuff that is strictly on screen, just to make sure I don't break things. But then we have a basic plotting software, and we can plug stuff into it, and hopefully it'll make sense. I feel like the lines weren't drawn. But we do have our quadratic curve, and it doesn't seem to break anything. Now, is it asking too much to get an exponent screen? If I can get like some sort of Gaussian curve. I don't know if C native is going to have that without importing something. But I don't see any lines. If I turn off the line function, is it see if I if I greater than 0. Whoops. It wasn't doing anything. It instantly failed. There we go. Now, why don't I see my red dot? Oh, you know what I need to do? This goes after everything. So this check is a little bit superfluous. It's not a little bit superfluous, it's absolutely superfluous. And then we're going to do cursor position. Want to make sure my plotting software is actually good before I actually do anything with it. Hey, there's my red dot. Not bad. I tried to blank the screen and it did. Okay. Let's make the Joe print color something different. I'm going to think green. Okay, that's an option. And then we'll get right into the physics stuff. Green. There we go. Okay. So, now let's actually move on to some physics of what we want to actually try doing. I promise quantum mechanics, so we have to go and look up what that means. So we're gonna have what's a good drawing for? Let's do a quick Google. particle in a box. There we go. If I can zoom in, try to straight what's going on. There we go. So, this is a little bit overproduced, but essentially, what we're going to do is we're going to trap an electron inside of a place that it can't escape. So there's going to be, we're only looking in one dimension, so we're only looking, the electron can only move in the x direction. We're going to say, at the wall on the far left and the wall on the far right, the electron absolutely cannot exist there. But in between, because it's a quantum mechanical object, it has a probability of existing depending on whatever wave function that it's defined by. So the higher the value of the wave function at that point, the more likely it is to be there. So what we're going to do is we're going to solve Schrodinger's equation to find out how likely the electron is going to be at each point that we're going to sample in space. So in this case, the edges of the screen, we're going to say, are the edges of this box that we've trapped the electron. And we're going to try to use a numerical technique called the shooting method to figure out the solution to this equation to find out this probability amplitude, what we're calling this, wave function. I'll take questions at any time. I'm not sure if I'm actually lost. I know there's 7 people in stream. I don't know how many of them actually know what's going on. Following along with the code stuff. So, okay, yeah, we're gonna be plotting psi-squared at some. Yeah, so we got 2 opposite ends of expertise here in chat. So, yeah. So going back, we're gonna look at, oh, everything's all zoomed in. Looking at this. No, not that one. This one, simple one. Okay, I try to zoom in and it. Where are you? Too simple. There we go. Exactly simple enough. I mean, it's to say 2 places is a little restricted. The electron is distributed over a continuum of spaces. Okay, that's not the right way of saying that. At least not to the layman. Essentially, it's not like there's one place and another place that it can be. It's just a smooth distribution. Well, I mean, once you measure it, you either know where it was or how fast it was going, depending on what measurement you. And then it's whatever. After that, you're kind of lost as to that. So at the point of measurement, you know one of those 2 things precisely, or a mixture of those 2 things, according to a certain inequality. Yeah. Well, there's. I mean, electrons are not very distinct from one, at least not without certain conditions. They only have so many properties, and you have 2 electrons with the same property, you can't really tell the difference between them. But as far as saying that's it in 2 places at once, that's just a kind of a way to explain that it's not in one place. But 2 places is a very specific situation. Yeah, so fermions, they can't overlap, but that's a different thing. They're just down to the basics. An electron, when you're not actively measuring it at that instant, for every other instant, it's kind of spread out over space in terms of where it could be, or where it effectively is, or at least part of it. So if we go back to this picture here, and we go look at E, can you guys see my mouse on here? If you can see. Okay, it looks like you can see my mouse. There's many electrons in the universe. They just all kind of interact with each other. Well, to get a Nobel Prize, you actually have to show something in an experiment. It also helps if everyone else likes your experiment. But basically, we're looking at one electron here, but there's many positions. We can chop up space as much as we want in between these two walls and come up with an infinite number of unique positions. And we say that the electron is at least partially in all those positions, except at the edges where these two walls are. So the idea is that we're gonna do a numerical computation. So we're gonna chop up space into a certain number of bins. In this case, 320, and hopefully that bin size is enough to get us an accurate result for what we expect to see the electron do. Pedro, you keep bringing more and more stuff into this, and you're just gonna make them lost. I don't think they know what a de Broglie wavelength is, as far as how it applies to this. Okay, you guys have Google, but as far as we're deep into the lay field here. These are a bunch of people that know coding well, and they maybe have a good grasp on mathematics, but I don't think they've ever taken a quantum mechanics course. Yeah. Okay. See, that's our starting point. Our starting point. So, what's an electron? Okay. Anyways, so let's explain as we go. So. The electron, let's just say the electron is going to be this wave function that we're going to plot out. Let's forget the physics of it now and just look at the math. The electron has a wave function that describes where it's supposed to be or how probable it's going to be at this point. And then what we're going to do is we're going to solve this differential equation here. So this is not too different in terms of mathematical rigor from doing like basic kinematic stuff. So like if you want to program in something ballistic, like your character shoots out a gun like in Worms, and it has to follow a ballistic trajectory, you're solving the forces on that bullet. You're still doing this second order differential equation. This version of it looks complicated, so I kind of simplify it here in Word, make it a little bit more digestible. If I zoom in the right amount. So if we just simplify into one dimension, which is kind of what we're used to doing most of the time, like when we do the physics on like say a bullet or a ball or something like that, we drag it down with gravity, and we push it forward with velocity and stuff like that, and that's this class of equation, more or less, when we have the second order derivative. Okay, so for now, I've simplified that equation, the Schrodinger equation, into the one-dimensional case. We only care about the x direction. We're not thinking about y and z. We assume y and z same everywhere. Oh crap! Sorry. Yeah, I do need. I've got a desk USB mic, and I need to get like a real, mounted mic, a suspended mic, or something like that at some point. So, numerically speaking, we can go over and we can look at these the finite difference approach. And we can do derivatives of finite difference, and we should be used to this already. So anytime we do velocities in our game engines, we always talk about our delta t's. So in this case, this would be like future position minus past position divided by delta t. And we work our way backward, say delta t times velocity plus previous position is future position. And we've done this before. We've had to do something like this when we did the collision on the box in Sinusoid. So going to higher order difference. There we go. There we go. So instead of doing a first derivative like velocity, we're doing a second derivative. So that's like an acceleration. We're going to be doing something like this, where we have our current position, our past position, our future position, determined by our delta squared. In this case, we care about our delta x as opposed to delta t. Got this little cofactor in front. That's just going to be some numbers. It's going to be floats. We're going to take care of that ahead of time. And we have a potential energy and the electron's energy. Potential energy is defined by the environment. It's, in this case, we're going to say the walls have infinite potential energy, which means they're rejecting everything. making sure nothing can penetrate them. So that's the walls of our box. And everything inside of that box has 0 potential. So it should be relatively easy to simulate. This stuff is just going to go to 0. And the energy is what we're going to have to guess. We have to figure out what energy the electron can be at. And we'll know that the energy is right because the wave function will come out in such a way that the electron is trapped in the box. If the electron is not trapped in the box, we have the wrong energy and it can't be at that energy. Okay, so we're just going to do a little bit of manipulation. We're going to replace it with our finite difference here to make that numerical approach. And we get all this stuff on the left, plus potential term, plus energy term. And then we're just going to find out what our index is in the future. So in this case, I centered it around index I+1. And that's going to be kind of like our current index. And I is going to be our previous index. And I+2 is going to be our future index. In this case, we start out at I+1. And we're trying to figure out what's happening at I+2. And we can find that out by taking the I+1 value and subtracting out the I value with all these factors involved, which we already know all of except for E. We have to guess E. And that will produce the next value. And we keep going in order and keep doing that over and over again until we get to the end. So, that's the mathematical, numerical, computational basis for what we're going to try to do tonight. What is this? I don't like that. This is from Phantasy Star, though. Well, there we go. Jungle Joyride. That one. That stays on the playlist. So, let's take this crap, and we're going to put it in C. So, first thing we did, let's call this our, just load up our constants ahead of time. So in this case, instead of doing 320, we're going to do 10 nanometers. We're making a box that's 10 nanometers wide. We have to be small because quantum mechanical effects only happen on that kind of scale. Our DX is just going to chop it up into 320 spaces. 320 bins. We already have the X predefined here. I'm going to go ahead and this out for now. We're going to have our initial X values. Or sorry. Let's call it our initial Y values. The Y in this case is our wave function. So that's the psi that we saw earlier, Greek letter. But for now, I'm just going to call it Y because the code's already there in Y. So Y at index 0 is 0. Float. And then Y1, we're going to start it off at like, let's call it 1.0 E minus like 10 or something. Something small. Something manageable. Because it's going to explode soon. I think I saw that in the Discord for That's It Guys. The I don't know. It looked like it was like eggs and some sauce or something like that. Everyone's becoming a cook now that that everyone's trapped at home. Not great for the restaurants, but it's probably better for our diets than whatever before. Okay. We need one more thing. We're gonna have we're gonna need some constants. We have to bring in some physical constants here. So let's go look up Planck. Is it with a CK? Planck constant? Planck? There we go. And I try to do everything in SI units. So there we go, joules and seconds. So let's just do some quick unit analysis. Let's do units. So we have our meter. We're going to call that 1. We got our second. And I'm going to call a kilogram 1 as well. And that's going to... I forget what the base of that unit is. I'm sure Pedro can say it. Oh, come on. You can do better than Cookie Razor. I've got some celery sticks in the fridge I've been working on. I mean, you better be doing... I saw on Reddit the Schwarzenegger quarantine exercise where basically just gives everyone a calisthenic program say, you can do it. Probably not in that accent exactly, but you know, basically that. There we go. Nigiri. Okay, yeah, that's probably okay. So we have our units here, and then we have what's a joule? A joule energy. That's gonna be kilograms times meters divided by second. Let's avoid as many divisions as possible. Okay. Joule, we got joules, we got seconds. That means we have our Planck constant here in joules second. We probably also going to want electron volt, because that's kind of like the unit of scale unit that we're used to in terms of quantum mechanical effects. So we'll do an electron volt is that number, E minus 9, float times joules to keep it consistent. Right? We're also going to want our electron mass. That's the M term there. Okay. Thank you, Google. Oh, let's float centimeters is equal to 1.0 E minus 9 F times meters. Okay, there we go. We don't need that anymore. Then we have float mass of electron. This number. E minus 31 times kilos. There we go. And we get everything in SI. That way we can divide out units in SI and display whatever we want, and it just kind of works out for us. I might go to the store, get some sushi rice, and see if I can make my own. I know the Asian market is still open, it's still well stocked. I know that I've been trying to go to Winn-Dixie and Publix, and meat has been difficult to get. No reason you can't. You can just define a variable in terms of another variable. So if you wanted to you define all your units. This is what I do anytime I have a physical simulation I need to do. Is I just define my base units so I can do everything in terms of my base units. So I know how big everything is. And if you want to find out how big my width is in terms of nanometers, I divide out nanometers. If I want to know how big it is in terms of meters, I divide out meters. What's a madras? Multiple letters? Oh yeah, you can always have it's always had multiple letters. Oh. I like the yellow curry. Yeah, I try to use only Sonic Team-based music because I know they're not going to take down my videos because of it. And PSO has a large library of good background music. And then every once in a while, I get surprised by like the invincibility theme from some Sonic game I added in here, and I have to take it off. I'm still pruning this playlist. I started at like 24 hours worth of music, and now I'm at like 19. Okay, what else do we need in here? We need Planck's constant. Why isn't that in here? I'm going to call that H bar. Where is it? Oh, no. I knew we had it earlier. There we go, Planck. So we want H bar. I don't know if we're going to want pi in there as well. I mean, it can't hurt. F times joules times seconds, right? Get that right? Joules seconds. All right. And also pi to as many places as it'll let me. Float I is equal to F. Go, and it's unitless. Okay, got our constants. Let's call this sim parameters. Oh, you know what else we're gonna need? We're gonna need a sorry, not voltage. I mean, you can think of it as like a voltage because of the electron potential, but it is the potential energy. That's gonna be units of joules. So we have to pre-build voltage. Sorry, potential energy. I keep doing. We have our initial. Let's do our initial. Let's just call it our potential. So for I equals 0, I less than 20, I plus plus. We're gonna have what are we gonna have? We have v. We're just gonna set v equal to 0 and assume that it's going to go to 0 outside of that. I is equal to 0.0 f in terms of joules or electron. Well, let's do electrons. Not in this version, no. You can do time-resolved Schrodinger's equation, the time-dependent version, and that tells you how things change over time. But right now, we're looking at these bound steady-state solutions. What am I missing here? I have our width, my dx. We have our potential energy. We have our initial y. So I guess now we can start talking about the shooting method. And that means we're going to zoom through thing is we're starting at 2, right? We'd have y of I. This is so in this case, I, if we go back here, the I is now at I plus 2. So this, I kind of confused the, yeah, whatchamacallit, the notation here. So let me just fix it real quick. So I plus 2 is now I, and that means I plus 1 is now I minus 1. And I is now I minus 2. So now we just see how the indices are behaving right now. In this case, this is going to be 2 times 1 minus all this stuff. Let me bring that off to the right side of the screen. You guys can't see it, but I can. Just to make sure I can write everything correctly. So we're going to have... let's go ahead and set up my... I'm going to call this my coefficient. And that's going to be equal to mass of the electron times dx times dx. Oh, it's -2. Forgot about that. Negative mass of electron times dx divided by h bar times h bar. Now this is very expensive for the Saturn to do, but if I combine it all into one thing, then at least the next 300 times I do it, it'll be cheap. Hey, VBT Senpai, thank you for noticing us. Came just in time for us to start actually doing physics. I spent a little while, probably about an hour or so, setting up a plotting software based off of Joe Engine's samples. Okay. This feels a little bit aggressive. Let me try e to the minus 1 and see how that goes. Yeah, that's basically it. It's just me figuring out how to get things to plot on screen the way I want them to. Okay. So we're going to have our 2 times, or float 2, so 2.0 f times 1 plus coefficient times our previous y, so that's y minus 1, minus y minus 2. Okay, just double check and make sure that tracks, and it looks like it does. Okay. So the shooting method here, oh, you know what I forgot? I forgot. See, the coefficient is multiplied by e minus e sampled at I minus 1. So what we need, simulation parameter, we need to guess what e is. So let's go real quick and cheat and go to hyperphysics, a particle in a box, and use their calculator to figure out what the first energy level for a... Oh, okay, yeah. So... I didn't want to have to actually do math right now. So we have h squared. Oh, I need to put in Planck's. Okay, let's put in the actual h then. Oh, whoops. I was about to make a mistake, I think. No, right. Float h equals seconds e minus 4f. So let's try to do the exact solution, which is h squared over 8 divided by... Okay, h squared divided by 8 divided by mass of the electron divided by the width of the box squared. Okay. H times h divided by width times width. Okay. Times mass of the electron times what was the last bit? 8. I keep hitting that. Now I'm wondering how slow this is going to be, because it feels like it's probably going to be a little bit slow. Let's find out. Oh, of course things didn't work out the way I wanted. Let's see what's going on line 94. Oh, the negative character is not quite what is supposed to be written there, because formatting or something. Yeah, copying stuff. Yeah. 109, I is undeclared. Oh, it's a silly mistake. Unused variable pi. Oh, I don't care. It'll be used eventually. It's undeclared in 119. Okay, fine. Whatever. It got to the point where it started graphing, and then it gave up. So what's up with that? It was sampling the one in the middle, too. Oh, you know what? I forgot to define x. Is equal to 0.0f. X for I1, and then I should be equal to I times dx. Oops. I should have defined v over here. Actually, that's the perfect place to define x. What am I doing? Now, we're going to come up with one more problem, and the problem is that we're expecting a unit for each pixel, and we don't know how big the actual distribution is. Hang on. Oh, and same thing with the x. So everything is too small to actually plot. So what I need is a plotting function. So what we actually want is we're gonna want width or dx, one of these two. Find up here, and then we'll set it in the main function, and that way we'll know based off of this x defined by dx. And what that's going to do is it's going to force the x values into their proper place, because we are rescaling everything. Before, we were doing everything over 10 nanometers. It's like 1 to the minus 8, and we're expecting units of 1. So the program is not going to be able to show anything interesting. So we spread these things out. And then let's also get a dy going on, or the pixel size in y. So once we have shooting method on y, what we're going to do is we're going to say y, we're going to find max on y. So float max y is equal to 0.0f. Okay, yeah. And then we're going to loop through all the y values. Find the biggest one. I is greater than, or yeah, just greater than max y. Max y is equal to yi. And then we're going to say that dy is equal to max y divided by 224. See if that actually works. As we did the first time. Oh, there's errors. Max. Undeclared. Oh, whoops. Screw and thumbs. Okay. yi. X. Unused variable pi. Invalid value in assignment on 133. What did I do? Oh, okay. Clearly, I'm just being sloppy. That's me. That's my fault. Okay. I forgot to rescale y on the plotting side. Okay. Let's try that one more time. We're going to do the same thing we did for x, except for y. So I divide dy. There we go. That's there. That's there. That's there. Let's go ahead and use that too. And you. Yeah, we're gonna want that. Who else is missing? This. This. Yeah, that sounds right. Dang it. What's going on here? Oh, this thing's frozen. That's also a bad thing. No, it's not frozen, it's just slow. But why are the values so small? I would like to be able to sample how big dx and dy are, but I can't think of a good way of displaying floats. Oh, maybe the absolute value will help here. Not sure about that, but it might. Declare variables with rescaled values in the for. What are you talking about? Line drawing for. Yeah, I probably could have commented this out a little bit better. It's going to be draw a line if on screen, and draw a line if both points on screen. So let's see, y by dy, y divide by dy. Okay, so, I'm not sure if I understand what you're going for here. Just give. What are you talking about? Declare variables with rescale values, like Okay, yeah, I could do that. But that would be a lot more manipulation. But actually, I guess it would probably make about it. Let's do that ahead of time here. Let's let's make a Y scale and an X scale. Okay, so there we go. Fine. Okay, we found max Y. Okay. I guess we found our dy, but we're not going to use that. What we're going to do, we're going to go loop through it again. And instead, we're going to define our Y scale. Y scale I. find scaled y is equal to yi 24 times yi divided by y max. And let's make that an int. And same with x scale is already an int. XS. Okay, that's probably good. Good suggestion. Good idea. S. Let's go back and undo the thing that I did. Yeah, you're right, because floating divisions on a piece of hardware that doesn't have floating division acceleration can be cumbersome. This one. Definitely makes things a little bit cleaner to read. Okay, so everything should be already on an integer scale, and it should be scaled. X should be scaled from 0 to 319, and Y should be scaled from 0 to 223. 3 or 220? Probably 223. Hopefully. Based off of our screen size. Okay, that should be everyone. Me add in the S's. Otherwise, I was gonna have a bad time. There. See how I screwed this one up. Most people in the Saturn community right now are working on something, I think. I don't know if we're taking a little bit of a break. High values still aren't there yet. I got some stuff at work I gotta do, but after that I'm gonna try and get over to doing some 3D stuff in Blender with the Great Value Engine again. I'm going to take a 30-second break to go and get a drink of water or something like that, and you guys can help me brainstorm why the Y values don't seem to be coming out correctly. Oh yeah, that's right. Pedro is running for office right now. I think you mean plug. Bump would be like bumping a post back to the top again. Okay. So I'm left with the other option that my shooting method is somehow incorrect, which is very likely. So instead of the shooting method, let us attempt... Oh, here's one way I'm guaranteed have at least 1 point where it needs to be. I'm going to make y equal 1 higher than it should. Or y at index 1. Okay, you see? Something's wrong here. Let me go ahead and scroll all the way back so I can show you. Okay, you know what? It's probably faster if I just set it x0 and there. First position 0. Okay. So I manually set. Oops. I manually set y equal 1 at 10. However, it went back down to 0, which means something happened, caused everything get down to 0, which doesn't make a lot of sense to me. So, instead of that, let us instead do strictly incorrect yi is equal to the previous one times 1.1. Okay, and what this should do, there we go. What this should do is it should gradually increase my y several times. Should be I minus 1. That way, I know what the end behavior should look like. It should look like something that steadily increases. And whatever the max is, that sort itself out by the end of it. Great. There we go. I mean, that's a little rapid, but okay. I mean, it's an exponential growth. Semi-appropriate for what's going on. Now, what I don't get is how it veered off to basically infinity. Before it got to the end. Because everything should have been divided out by whatever the float needed. And maximum value. So whatever my maximum checker is doing is not doing it correctly. Oh, sorry. Do I need to up the gain or something on the mic? Sorry, I was probably leaning a little bit too far back on there. But my point is that because that exponential curve is ending early on the plot, so I'm finding the max incorrectly. Something is wrong with my max. But it doesn't make sense, because I'm checking all the y's, and whenever it gets bigger, I rewrite the max y. Actually, what's the limit on float? What's float max? That might explain stuff. I was hoping for a single number response, and I'm getting a document. It should be pretty simple thing to look at. Maximum finite representable floating point number, 2037. So maybe I was a little bit too aggressive and I went out of bounds. So let's try 0, 1. Slower growth rate. Because I don't think I'm hitting 1E37 based off of that growth rate. That's too fast. Only increasing 10%, 320 times? See, now it's too slow. It's not going... Actually, that's wrong. That is very wrong. Number 1, all these are 0, which means max has been something wrong here. let's treat max y. Where's float? There we go. Max y. Let's treat max y. Variable we're actually going to keep track of. We'll find out what it is. We'll just cast it to int just to do a quick sanity check. Max y. I was hoping to actually have this working by now, but it's always something. I probably should have put it one line down, but I did that one up. Yep, that's what I figured. One line down. I'll just max y equal to. So I had a perfectly nice graphing utility that suddenly just broke because floats are going all over the place. That's a really large number. That's not 1e37, but it's still a large number. How did it get that big? Okay, maybe the growth thing isn't Is there a quick sign in Joe Engine that I can use that actually takes in there's some math stuff going on here. Try sine, square root. Oh, there we go. Floating cosine. That means they have to have floating sine, right? Oh no, it takes. That's not what I was looking for. I was looking for float as a. Oh, there we go. Cosine takes in float and outputs integer. That's not what I wanted. I want float in, float out. That's what I'm looking for. Oh, okay. I'm not going to try and pronounce that name. Aliwix? Okay. What we're trying to do is we're trying to simulate the quantum mechanics of putting an electron in a box, just to start out with, and then we're going to do interesting stuff. Right now, we're having a little bit of trouble making sure that we can actually display the plot we're trying to display, and it has a little bit of to do with the fact that Saturn's not great at floats, doesn't have a lot of float support, and I'm trying to use floats because I need the order. But essentially, we're going to try and recreate where actually this is probably a better picture to use. We're going to try and recreate the distribution of electrons, and then we're going to try and have our program calculate the energies based off of trapping them in this box. Oh, okay. Joe sign rad F. Okay. Actually going to do what I want. Got distracted. Where's Joe Engine? Joe sign rad. Okay, float in, float out. Okay, there we go. So let's do x times pi over 2. Nice catch. Thanks, Super Ray. And then we're just gonna call this. Let's call it 1 for now. And right F. Good thing I have that pi in there. Pi times xi times 0.5 f. So this should trap us in the right location. and then multiply that by 224 float to get us to the top. To be honest, I have no clue. I haven't tried including the native C. Seriously? Something's definitely wrong with my max finder. Something definitely wrong happened. Maybe it's the absolute value. I think the absolute value can't take in the float. In fact, that's almost certainly what's happening here. Oh boy. Let's just try a nice, simple, naive comparison. If it's bigger than the value I had before, which was 0, it will overwrite it with whatever it was. In this case, the first thing it should find at I equal 1 is 1, because I put it up over here. And this sine function should be able to go all the way up to 224. Right? Yeah, this looks right. Actually, no, wait. Is this in radians or in radians? Okay, so I put it in pi, and I forgot to divide out the width. Smart person. Whoops. Are they going to work on an arrays? Because that's what I really need it for. But for now, let's try this. There we go. This is exactly what I was looking for. Yeah, I know, right? A little bit short. Let's take away that half pi. Let's take away this prefactor, and then let's have this guy be 1e minus, I don't know, 2. Let's see if the max finder is actually doing the job. Hey, what's going on here? Why didn't you change your... Also, why is the top red? That. X finders, bro? No. Oh, you know what? It's because I know why. It's because it's cutting itself off at 223. There. But here, this shouldn't even be in the fourth. It should be after everything. But it should be wrapped in this condition. Let's make less than equal. It's for funsies. Oh wait, that's the wrong one. Wrong. Oh, that was okay. All right. Okay. Let's try that first. But also, what's going on with the with this thing? Let's try 2 pi. See what happens then. You get some oscillations in it, right? $66. Yeah, just 66. Oh, this should be cursor position X. Okay, there we go. So that's the positive bit, and the negative bit is off screen because it's negative. That makes sense. Okay, so maybe the max finder is working correctly and the shooting method is not suited for the Saturn. Kind of what I expected. What's the smallest addressable float that I could reasonably do? Would it be like... Wouldn't be 1e minus 37. That's not quite how that works. So, should I do like 1e minus 30? Oh, more importantly, there's this issue here with... That could be. What I'm worried about is that E minus 34 might be stressing out the limits of what I should be able to expect the simulation to do. Oh, what's this? Oh, okay, you have the math. I already had that open. Okay, so J float epsilon. Float minimum possible. Oh! Nice. Float min. So let me just do 5 times that, just to be safe. 5.0f times that. Well, I mean, you want a little bit of room to work with. Maybe I'll go with... Yeah, 5 feels right. 5 feels right. Because I want a little bit of room to work with. I'm worried of division errors between big numbers and small numbers and stuff like that. Because, again, we're going to have... electron mass is going to be like minus 31. And then h bar is minus 3. Here's our problem. H bar squared. That's an issue. Yeah, you should be able to multiply floats. That should be fine. Even on the Saturn, should be fine. I'm realizing that h bar squared might be well past the float minimum here in terms of what I'm allowed to do. So we have to be creative. We have to change our unit system. So Planck's constant is a little bit less of an issue in electron volts than it is in joules. So let's try that. Let's make electron volts equal to... That doesn't feel like a very big float at all. That's incredibly tiny. That means the numbers I'm using are... even if I change the units here, it's going to be tiny. I only have 10 to the minus 5. Okay, it's used for comparison, but I can still get smaller, though. Whole point of a float. Right? I would think so. Yeah, it is a huge value for it to being the smallest float you can get. Okay, I should be able to get to minus 37. So, just... even still, so minus 37, that means this will barely fit in, right? For this H-bar. So let's go over into units of electron volt. Take away joules. I'm going to take away this H and H bar. We're going to make a new H and H bar. It'd be E15. Or less than last time with those tricky lines. times electron volt times second h bar. H bar, where are you? Right in front of my face. I just forgot to look at it. This E minus 16. So E minus 16 squared should be 32. That should be able to get me to the minus 37 boundary without issue. I hope. But then a kilo, how do I compare a kilo? Let's look up real quick the electron mass in different units. Just in case. I don't want to have to divide out c squared, that's just asking for trouble. Let's keep it in kilos. That means what? What does that mean for my shooting method? Let's go to the coefficient. So we have e to the minus 31 times... Oh, this is already pretty small. Idea. Let's do float. Yeah, this is the part I was afraid of, because I can do this on a normal computer, and it'll work. The problem is dxh equal dx divided by h bar. So mass of electrons already tiny. E minus 31. Oh, that's going to be untenable, isn't it? I don't even know how to deal with that. We have minus 37, right? So we're going to have E minus 37. Let's just handle this real quick. We have minus 37. And then this dxh is going to be 10 nanometers divided up into 320 parts is going to be basically like having 10 to the minus 10 to the minus 8 split up 320 times is basically like having 10 to the minus 11 or 10? 10 to the minus 10. Let's call it minus 10. But then we divide out the h bar. The h bar is at 16. Now we're going to have plus 16. That's going to give us 10 to the 6. And now we're going to do that twice, and that's going to be plus 6, so that's 37. Not 37, sorry, 31. Plus 12. It's 29. And 19. So we have minus 19, which is tenable. Second issue. For my initial energy guess, H times H, dangerously small. H divided by width times H divided by width. Divided by electron mass times 8. I'm hoping that this fix will be enough to do something, but first, let me just make sure I'm doing things correctly by double checking my plot. There we go. He's undeclared. What else was wrong? There we go. That's one hump. This is what we expect to see when we finally get this thing working the way we want. Now, what's the next thing I want to do? Let's try, before we move on to the actual physics simulation, I want to make sure that this thing's not going to break on me. Let's try doubling the frequency at Sinusoid. And when we do that, let's also check for min-y. Go ahead and add that in. Fine. Okay. And we're going to do 2 checks. We're going to be doing a max, and we're going to be doing a min. And we input that here. Let's run that again. That should give us is both humps, right? Positive and negative? No. Unfortunate. Okay. Oh, I need to add the min y on top of y. Whoopsie. Or subtract. My mistake. Making these silly mistakes I should be making, but a little bit out of practice. There we go. Positive and negative port. Of course, it's not going to say that because I'm printing out the coordinates on the screen, but now we can print or plot the whole thing. And this should be one of the energies that we expect to see. Now, let us attempt to do that again, but this time with the shooting method. I know, right? Now let's break it by trying to do something real with it. So just to double check, my coefficient is... dxh times dxh. Because we have to kind of optimize the way we're doing the divisions here to make sure that the powers are adding up properly. Which is what I did with this this initial guess for E here. Now let's also do 1 times 1. That'll become important in a second. So if this actually works properly, let me just double check. Make sure I'm not going crazy. So that's going to be 2 minus 2 times the mass of the electron times dx squared divided by h bar squared. What did I write over here? The 2 minus 2 times mass of the electron dx squared over h bar squared times E minus V. In this case, where's E minus V? Is our guess. V has been set to 0 over here. And previous and previous. Right? Yeah, okay, minus. Good, okay, I feel okay about that. Try it. Let's try it and actually compile this time. Will it work? Holy crap, it worked. No. Yes! Yes, it worked! Okay, so I know it looks the same as what we just did, but what we just did is this is the computational results of trying to find a particle in a box. So this is actually what we expect to see for the probability curve of the electron in its containing box. Okay. So, it doesn't look impressive now, but let me show you that this is real and not fake. So the shooting method should be working, and it just required a little bit of finagling with orders of magnitude to make sure I didn't go outside the standard, which we can take a look at the end of the day, but I'm too excited now to jinx it by looking at documentation. So, let's try int n, and n is going to be which number state we can be in. So let's go back and look at the physics again for once. So the quantum part of quantum mechanics basically means that instead of having any energy we want, we can only get a certain list of energies. And this list of energies is defined by whatever boundary we have. In this case, when we have the box's boundaries of infinite potential on the left and the right, which forces this probability function to be 0 on the left and the right, means that our energy levels has to be this form. So n squared times Planck's constant squared divided by 8 times the mass of whatever you're putting in there, in this case the electron, and the width of the box squared. So I put in 1 for n squared. That's that 1 float times 1 float I put in ahead of time. And what that gave me is n equals 1. That's that bump that we just simulated. Okay, now we're going to do n equals 2. So for n equals 2, hopefully multiplying ints by floats won't break this thing. N times n. Let's see what this comes out to. We should get 2 bumps, right? That's what we're expecting. Two bumps. Okay. And if we want to find out the actual probability of finding electron there, because that second part of the bump is negative. So what does negative probability mean? That's just accounting for something called a phase. I'm not going to go into it right now unless you guys really ask about it. But I'm doing it. Oh, yeah, I've done it. Oh, I've done it. I was doing it, now it has been done. So yes, I've done it. Okay. So anyway, like I was saying, that second bump, the negative part of the bump, that's just accounting for something we call phase. But the amplitude is what we care about. So what we're going to take is the amplitude squared. And that's going to give us our actual probability at each point. And I'm going to do that over... Where are you? Okay, we do the shooting method, and then we're going to do... I'm going to just call it psi squared. Psi squared. Start from 0. Start from 0, go up to 320, and yi is now going to be equal to yi squared. And that's going to get rid of any negative values and what have you. And the psi squared that we're calling it. So basically, this figure over here, squared, is the actual probability of finding the electron at that point. So hopefully that means, let's go ahead and switch this over to the third order. So n equals 3. There we go, 3 bumps. So what this is saying is that at the edge of the box on the left, the edge of the box on the right, and 2 points in the middle of the box, there is no chance of seeing the electron there. But in between those points where the electron has 0 chance of being there, there's 3 points that the electron has maximum probability of being there. So that's kind of like what we were talking about earlier. Someone mentioned being able to be in 2 places in once. There's a continuum of places that the electron can be in. But there's some places it absolutely can't be in. And if you want to split up the places you can be in by all the boundaries where you can't be, then you can kind of say the electron can be in these 3 zones. And when you measure it, it's going to be in one of those 3 zones. And it's definitely not going to be at the places where the function goes to 0. Okay, so we are able to put in a good guess for energy on the shooting method and get back a wave function that makes sense and that corresponds to what we're expecting. So, what happens when we're off? So let's go ahead and look at why the shooting method it still requires an extra bit of coding here. So let's do n times n plus, I don't know, 1. So instead of 9 times all this stuff, we're going to get 10. This is going to throw things off. I don't know if it's going to break it. Probably not, but it's going to throw things off at least. There we go. You see? So now things aren't working the way they should be. At the edge of this distribution, we have the electron being potentially on the boundary where it's not allowed to be at. So we define the space as it's in a box. And the box has walls, and we said the electron's not allowed to be inside those walls. So by saying that, what we're saying is the probability of being on the wall is 0. This simulation result says, hey, I'm on the wall with a not insignificant probability, which is telling us the energy that we guessed was wrong. So part of the simulation is telling the program how to guess the energy correctly. And we figure out what the correct energy is for these states that are supposed to be bound inside these systems by saying, well, if you run through it and you find out that the last value for psi is as close to 0 as it can get, that means, and we've done it correctly. I'm not sure if we want to do that tonight, if we can pick this up again another time for actually doing the search algorithm. Depends on what you guys are feeling. I know there's a fair bit number more in chat than I was expecting, so it depends on what you guys feel like. I did want to try and do another potential well situation. So let me just call this float E hardened off and just do something called a simple harmonic oscillator. So for the simple harmonic oscillator, let me see. I mean, if that'll take a little bit more time. Maybe if I work on it on my own and I'll release it, I can do like a, you know, run quantum on your Saturn if you want kind of deal. I'll think about it. So what we want is let me see. Let's go over to Wolf and have it do the math for us, because that's an easy way of cheating. We want a quadratic potential, so that's going to look like x minus a, or sorry, a times x minus b squared. But b, in this case, is going to be, we have a 10 nanometer wide space. That's how we defined it. So let's put it right in the middle. So let's call it 5 nanometers. Such that, so y is equal to this. 5 nanometers. And that y of, oh, I know. This way. Actually, I could probably do this in my head now that I think about it. Y of 0 should be equal to 1 electron volt. It should probably be like 1/5 electron volt for that A value, right? No, I didn't want to solve it for me. Probably help if I actually spelled. Yeah, it doesn't want to do it for me. Okay, but basically, if I make 0.2 float times electron volt times whatever the x value is, I mean, I guess I could do a quantum demo type thing if I really wanted to. Yeah, that would make some amount of sense. Let's do 1 electron volt divided by... how big is it going to get? It's going to get 5 nanometer. Right? Yeah, 5 times nanometer. Actually, it could be 25 nanometers squared. Think about it. Times xi minus 5 times nanometers. Do that twice over. So now we have to get a good guess for the energy value. Actually, well, now I'm here. Maybe we should plot the... should probably plot the potential well in blue. E divided by electron volt. Divided by electron. Times. Because that way you can see what's actually going on here. See, now I'm gonna be tempted to do a scaled potential, just like I did for the scaled Y value, but I'm already here. Wonder if that actually works. Actually, I probably don't need to put the pixel in the background if I just do the lines. So let's take that out. Oh, come on. 1 volts undeclared. Oh, that's an issue, isn't it? X error before float on 139. Oh, that's right. I gotta fix something. Yeah, let's just do 0.2 part of the way up the ladder. Now, is it actually going to draw my potential? There's a potential well, and there is the incorrect wave function. No, I want the overdraw. I want the blue to come before the wave. Because the potential well is in the background. Potential well is the setting. The actual thing that we care about is the wave function. And this is showing us that the wave function is incorrect. So what we're going to do is we're going to manually shoot our way up to find the correct wave function. Oh, you know what? We can make... I know what we're going to do. We're going to make this into a game. So, float E... is going to be equal to 0.001 F. Equal to 0.0 F times electron volt. Okay. What we're gonna do is, let's see, there's all this crap. Up and down. We're gonna control the energy levels with up and down. And we're going to do that in layers. So if I do up, we're going to make it go up by 1 millielectron volt. If I hold down A and go up, I'm going to make it go up by 10 millielectron volts. And B is going to be 100. And C is going to be... C is probably a bit much, actually. Do another 0 there. Okay. And we're gonna plot out our energy too. E times electron volt times 1000. Okay, so what I'm doing is I'm going to be able to control the energy level that I'm guessing with the controller, which means part of the draw function is going to be creating a new function where I perform the shooting method. And maybe we'll just leave out psi squared for now and just plot the normal psi. That way it's going to help us visualize what's going on here. I don't think I need this anymore. Remove all this stuff. Into something I'm going to call a function called shoot. Avoid it. But what I need is I need to define ahead of time my v. It's there, okay, and some of these main constants. Go ahead and put that up near the top. Down here. So what shoot is going to do is it's going to perform the shooting method at the energy level that I have selected with this up key or this down key. So now let's do if Joe key we want rest key A. Is that a thing I can do? E is equal to E plus 0.00 F. 1F times 1 volt. Okay, and then else if no else there we go. And now we're going to be able to manually with your controller sweep through different different energy levels and manually search for the correct energy level to create the wave function that obeys the right behavior. Now we're going to call shoot. Shoot should just take the energy level that you've guessed and run with it. Perform that shooting method calculation. And scale it. By scale? Okay, there we go. So the callback for the controller input, take care of this. And the callback for the draw, it will just draw whatever we tell it to draw. Minus, oops, minus. Now there's no way this is going to work on the first try, but let's see what happens. It's typical. Okay, line 42, initializer element not come. Is that a condition that I have to meet? Why is that an issue? Initializer's element is not... Why do I need to do... I mean, I'm setting it to 1 anyway, but... You know what? Screw it. Let's just do this. And then in Joe main, I'll just initialize it the way I want. Energy and or set parameters. So I'm guessing before the function starts, I'm not allowed to actually do what I want. But I can initialize them so that I can use them. So probably all this stuff is not sure until I set it up correctly later. And then I'll just initialize it in the top so I can call it wherever I want. Actually, I don't need to do that. Sure, whatever needs to be initialized up there is initialized, and anything that doesn't, okay. And the X has already been in there. Can't even use that anymore. Okay. E already been initialized. Now, will this run? Probably not. Okay. Initializer element's not. Oh, whoops. Probably do something about that on here. Not in shoot, over here. Equal to 1.0 E minus 9 F times meters. Occurs to me, I don't think I redid the shoot function on every implementation of that movement. Let's see. Oh boy, this is slow. Oh no, I forgot to... I gotta blank the screen when I do this. Go up. This is so slow, you guys. I'm waiting on this thing to update. Okay, first off, let's just make sure that I'm actually redrawing after I've shot. So let's, you want to clear the background. Shoot is happening, right? And my draw is being updated. So first off, let's there's station. Let's go back to the background. Clear background. There we go. Black. Blank and redraw. There we go. Oh, that's exactly what I needed to do. Look it up. Yeah, okay, well, now I don't. There we go. So, let's go back to making it so that, where did I define my... Here. Let's go back to the basic particle in a box potential and see if I can go back and guess what energy level I need to find. Okay. That's getting slow. 6, 7. It's that energy. It should come back down at some point. Maybe I need to add a C button for electron volt level. Maybe the box is too skinny. Or I'm jumping too big. So let's go back hyperphysics real quick. Plug in the numbers. Figure out what we... Oh, we have 10 times 10 minus 9 mass of 1 electron. Should have somewhere between 3 and 4 electron volts. Did I skip over it? No, the initialization is not the problem. It's just I'm not looking for the right energy. That's the issue. Just real quick, do you guys remember if JoePrintf can handle floats? Should be somewhere between this. What about fixeds? How do I print a fix with JoePrintf? Just had this working and now I don't because I wanted to for the right energy. Okay, so in this case, let's initialize the energy to the correct value. So it's going to be n times, okay, well, it's going to be, let's call it 1 times h squared. H times H should be H divided by width. H divided by width for our two square values. And then divide by 8 mass of electron. Find out what number it should have been. Well, that doesn't look right at all. Did I screw that up? I totally forgot about Megagon because of the virus thing. Each in the right. Each is in the. Electron is in kilos. Units of mass are incompatible here. Let's... Okay, fine. Let's just do it. Let's just do, let's just input C in here. For reasons. Go, and then we'll can't fix the messy electron. Times. Oh, I forgot about this too. Yeah. C is equal to this. Times minutes, times seconds. Okay, so let's go back and... Hey, where's the electron mass? There it is. So, 1 mega electron volt should... What? 1 million electron volts? Times 1 E6 F times electron volt divided by C divided by C times C. I don't understand what changed to cause the simulation all of a sudden to stop working. Still looks wrong. Let's add in a few more units here. We're gonna have milli electron volt, mega electron. So milli electron volt is equal to 1.0 e minus 3 times EV. And mega is equal to 6. Yep. Oh, whoops. I did this backwards. It should be divided by electron volt. %D. And here's how I'm gonna fake these units. So there's gonna be this minus the integer version of it. Electron volt. Okay, and then I'm going to divide it again by... No, I don't think that's going to work because I need leading zeros. Let's do that for now. That is still way too big. That doesn't make any sense. Also, the point, whatever, that shouldn't be there. So the energy should be Planck's divided by width times Planck's divided by width divided by 8 mass of electron. Planck's divided by width, Planck's divided by width, divided by 8 electron. Okay. That should be correct. So, we had it working before. It broke for reasons I'm not sure why, but they're happening. You try making the thing wider. Try nanometers and see what happens. That number still feels so very wrong. Why is it so wrong? Don't know if that's actually going to help. See. So something broke. You have to figure out what broke, how it broke. Oh, you know what? I didn't shoot the first time. I should shoot first before I start. Shoot. Well, which part's undefined? I don't like how that red dot now looks like it's pink. It's pretending like it's drawing over itself, I think. I'm pressing up. My energy counter is not changing. I don't like that. Constants. Let's see. Same place. Okay, so the chute coefficient. How do I define my coefficient? That defined. Oh, that's already defined over here. dx is width divided by 320. Width is 20 nanometers. So mass of electron times dxh times dx over h bar. That looks right. H bar has been defined, dx has been defined. Mass of electron has been defined. Oh! Oh, whoops. How did that happen? Let's get that down here. I don't know how that happened. How was I allowed to do anything? That would have been like a division by zero error, wouldn't it? Oh. I had the energy being calculated as a function of width before I defined my width. That's an issue. N is no relevant. Okay, try that. Here's the thing, Joe Engine, I believe, uses high work RAM, but it kind of uses it in a sloppy way. So I could literally have been just grabbing anything that was previously used in memory and no longer there. There we go. The number's wrong. That number is definitely wrong, but the curve is correct. So let's get that down to 10 nanometers and see if that helps. My cat is complaining for food or something, I don't know. Yeah, I was writing a garbage value to width, and I was using that for an energy calculation. There we go. That's what I was expecting. Now, I can't quite... if you guys can think of an easy way to display the digits leading in front of that, maybe if I just go to a smaller unit. So instead of millielectron volts, I'll go to next size down, not nano. Micro electron volt. It's not a parabola. It should be effectively sine squared, because that is the solution for the particle in a box. Let me create a micro electron volt. And then I'll define it as micro electron volt minus 6. And that way I can move on... Where's my gamepad? Let's do C, E, A, for 0, and the default case be one more 0 on top of that. Sine squared and parabola are distinct. I mean, I guess they look kind of similar, but they're not the same thing. I mean, for starters, it'll... Actually, that wasn't even sine squared. That was just sine, because I wasn't squaring it yet. I wanted to display something different. But it will... a parabola will continue on to infinity, and sine is inherently bound. So once you get to the point where sine starts to go to 0, curvature will change. Okay. Let's take that and replace it with that. Now it's minus. And now we can actually scan over different energy levels. Okay. We should be starting on the correct solution for particle in a box. Okay, so it's 3.760 millielectron. If I press up, going up by 1/10 of a millielectron, and it should start to break. There we go. Is it breaking? Oh, because the right side is going negative. Okay. So remember, the point on the left is defined as 0. The point on the right is going negative. You try to go a little bit faster. Oh boy, I slowed this console down. There we go. So what I'm doing is I'm trying to find where the... Oops, okay. You know what I need? I need a guideline to show where the 0 point is. It's trying its hardest, it really is, but the bigger I make the numbers, the harder it gets. So let me try to find the third mode. See, it's not even responding right now. There it is. So that's kind of close. So somewhere around 35 millielectron volt should be the third energy level in this quantum well. It's infinite well. Let me see if I can't find the fourth energy level, but it's probably going to start breaking because it's just not prepared for it. There we go. Come on, you can do it. I believe in you. A little closer. Something around. So what you can do is you can take out your physics textbook and you can kind of double check these numbers. What I'll do is what I want to do is I want to make this kind of like guideline. I'll take this guideline at the bottom. So let's go back and do the sine squared thing. Let's go back into shoot. Right, and reactivate that psi squared code. And now we can use that blue line on the bottom that's supposed to be potential energy and use it as a guideline to try and find out what energy we're actually supposed to be at. And maybe I can use the X, Y, and Z buttons as finer tuning on the number. Try and get exactly where I want to be. If I can find out what happened. There it is. So X will be 1 0 on top of... How many zeros am I actually going to go? So 1, 2, 3, that's millielectron volt. So 1, 2, and then 3 would be microelectron volt. Okay. A, B, C, and then backwards X, Y, Z smaller. So actually, let's make it so that you have to be pressing that X, Y, and Z button. And get rid of that else statement. So C is tenths, hundredths, thousandths, and then X will be 100 micro electron volts, 10 micro electron volt for Y, then 1 micro electron volt for E. That way we can get fine-tuned as much as the display will let us. Let's do the minus. Sure is trying, man. There we go. And now, now that we have a good feeling for this thing is actually working, let's switch back over to the parabolic potential. And then we can start doing things like switching between different potentials and redoing the whole thing with input. And that way we can have an actual live demo of different quantum well simulations. I should probably also put up the width of the screen. I mean, that's certainly an idea. Let's see. Oh, it's okay. So I need to go up higher in this well to try and find the right energy. Okay. Oh, wow. Okay, I've definitely gone too far. There's a lot of bumpiness there, and that's indicative of a high order mode. On. On. It is struggling. Oh, it's not writing over the old values. That's not good. Extra V there. Oh, negative. We definitely don't want negatives. Come on, up. Up. There we go. So Z, I believe, is visual mech. So let's try to get this on some sort of that's recognizable. Wait, this is slow. Okay, so we have a quantum system simulator right now. So we have a parabolic potential. We're trying to figure out what energy level we need to find in order to get a bound state. Something that actually stays inside the well. Makes sense. Something that the well actually supports as an energy level. Problem is, Saturn is very slow when it comes to floating point calculations, so we're kind of struggling on sweeping through the energy levels. Come on, lower. I think we're getting closer. I should probably know around what energy we should be looking for. Okay. So now let's try sweeping up in large numbers until we find. Or, I think the thing that's going to indicate that we've passed an energy level is that instead of going up to positive infinity on the right, we're going to go down to negative infinity. Oh, whoa, okay, close. Up closer. No, farther. Okay, colder. You almost had something. Go back down. Back down. Come on. Okay, let's try to approach closer. Okay, we're almost there. We're almost there. A little bit less. A little bit less. Come on. Oh, I forgot. We're doing y squared, so we're not going to see the negative behavior. We just kind of have to guess. Okay. I feel like this is close enough. So this should be mode number 1, 2, 3, 4, 5, 6, 7. Yeah, mode number 7. So, mode number 7 should have an energy level of 6.5. Right? Yeah. Mode number 1 is 1/2 H bar omega. Mode number 2 would be 1.5 H bar omega. So if we take whatever this number is, divide by 6.5. Let me get out my calculator real quick, because I'm not about to do math live on stream. Embarrass myself enough today as is. Okay. Oh, okay, you guys can actually see that. That's neat. Okay, so 507,400 divided by 6.5. So if we go down to 78061 or so, we should find our fundamental. The thing with one bump. Will that, Super 8, for that command, will it also clear any sort of drawings on the background? Is that clear everything? Because I'd rather use that than clear the background that I'm using right now. It looks like I'm redrawing a lot. I guess that's to be expected, I guess. Okay, so we want to get down to basically what was 78 or so. 78 mil electron volt. So I believe if I hold down B, we want to go a little bit further than that. Okay, C. 4 on 3, 2, 1, and 7. A little bit closer, come on. 87, 87, 87. Go down! Oh my goodness, it's so slow. 87. 77? Come on. 78. Up to 78. Maybe I should have it trigger on start. Like I'll, oh, what did I guess it was? 78061. On. Okay. I definitely need to separate input from the simulation so that we can put in a proposed number. Eight. 6. 6. On 6. Ah, crap. We didn't see it. Did I do the math wrong? So if we just look at simple harmonic oscillator energy levels. The first one's at 1/2. And we saw 7 bumps, which means n is equal to 6, so we got 6.5. So we divided out whatever the energy was by 6.5. Should get us down. Oh, that gets us H bar. We need to get half of this. Divide by 2. There we go. 39030. My bad. Oh, close. Okay. A little bit closer. Okay, maybe I was a little bit off. There we go. Oh, okay. So the problem is when you're this low in the well, the sensitivity goes up, and we probably need a little bit finer of a mesh to get the right energy level to make that thing on the right disappear. Found it. Dude, like the pandemic has got everyone's shipping lines just completely screwed up. So I would expect nothing that you expected ordered that needs to be made to be ready anytime soon. I mean, China had to turn off the country and turn it back on again for like a month period. Anyway, so what else can we do here? Let's try to separate the input from the output so we can actually use this and actually guess the correct energy. Let's go back to the input and so instead of clear background, what were you saying to use? I missed the command. Array, I think you told me earlier. Crap. I totally lost it. What was the, okay, Joe clear screen. Thank you, sorry. Joe clear screen. And let's just double check on the documentation. Make sure. Clear screen, useful print. Okay. Let's find out if that actually does what I think it does. Okay. I feel like that red dot is no longer serving a purpose, so I'm not going to include it anymore. And down, key up. What I'll actually do is I'll take key left and key right and use that to switch between potentials. Start. So we'll still be able to sweep through energies quite easily, and then we will force the redraw, or we will force the recalculation with shoot when we press start to make sure that we actually get to the energy level you want. What was the other thing I wanted to do? I wanted to be able to switch between potentials. So let me just do void potential. And then we'll just real quick take whatever our potential calculation is. And we'll have a potential ID. Int potent ID is equal to 0. If potential ID is equal to 0, we'll do we'll call this the infinite well. Else if actually let's do can we do a switch case? See switch case, that'd probably be easier. And case 1. Oh, okay, there we go. Switch O10 ID. Make sure I get the syntax right. Oh, forgot about this. This case 1 is a simple harmonic oscillator like this. And then default is just going to be 12. So width divided by 0.25f times width. Go. To make things a little bit more generic. Infinite width. And I'm guessing I'm going to need a break in there, right? Break on all the cases. Break. There we go. And now we can switch between potentials by switching our potential ID. Hey, Super Ray, I just caught that. What do you mean parameters void? Lost me on that. Didn't I put that in? Oh, there's clear background. Clear screen. Yeah, it's avoided. Go. Generate the potential first. And then we don't need. First off, let me cut this out. This should not be here anymore. And I will keep this here just in case. Let's see if this actually works the way I think it does. All right, that's neat. If I press right and start, no, start. Okay, start. There we go. It doesn't blank background. That's an issue. I still need this. And more importantly, on the print statements. The print statements up here. Potential. Okay, so when I evoke potential, it select something based off of potent ID. Okay, yeah, I expect. Okay, so yeah, instead of doing that, then I'll have and put that at the top of my draw. Okay. So if I can get it to switch between potentials, that means, oh boy. Okay, so I think that Go Engine's inputs are kind of lagging on me. What I'm doing here, which might be. Oh, there we go. So I am getting a little bit of lag on the inputs, and I don't know if that's Joe Engine or me utilizing Joe Engine. So let me do it so that I only clear the screen, and some form of. So the input would be here, 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 and of course here. Well, I mean. Here it's not really necessary, but and then oh, this is wrong. Not using cursor position anymore. In fact, I'm not using this red cursor anymore. I really need position variable. Okay, so now I can switch between potentials, and hopefully I'm not being excessively proactive with screen clearing. Okay. One. There we go. It takes a minute. Definitely takes a minute. So we said it was, what, 30... I forget. I think I had the calculator open earlier. It was basically 39 milliliters. The input is a slow part on this. That's the weird thing for me. So, me using Joe Engine's inputs seems to be slowing me down significantly. I don't get that. 3930? Oh, whoops. Fine. Close. Do it. Do it. So how do I push off the input loop to slave? I think that's what needs to happen. No! There we go. Okay. One more will do it. Draw. Now we have it in you. I definitely need to have some sort of screen indicator saying, hey, I'm thinking here. Give me a minute. I think if I were to continue this project, I would probably figure out a way to get the math done outside of floats. Or I could do that. That's like that. You know what? Maybe I should have the thing is it's the inputs that's killing me here, right? Or the draw. Which one is the worst one? Is it the gamepad or is it the draw? Gamepad for now. No, let's put it on the... Okay, fine, gamepad. Figure it out. Oh, crap. Wrong choice. Try it again. No! Okay. And we probably want to add at least one more potential on here just to make it interesting. So we have a simple harmonic oscillator. We have infinite well. Maybe we can put in a finite well. What? Okay, what's going on here? Why is the background not being cleared properly? Okay, let's do this. Let's put that at the beginning of the draw. That's the problem, because the Saturn is a multi-core system, and now I'm not used to having to deal with coordinating these guys. Oh boy, that's ugly. Can't we make this thing wait for V-blank or something? I thought Joe Engine already did that. Okay, that didn't help. Let's go back and put that back in here. Eating. Okay, I probably could have done better by using my own input code. What else is real? Fine. This is painfully slow the way this is working. If I remember correctly, I think it's around 3. I need another. Oh, okay. Guess it is getting late for... No, go back. Thanks for all the help, Super Ray. Oh yeah, I'll definitely keep this on the channel. Come on, up. Up! There we go. Try again. The number I had before. 39. Whoops. There we go. We can kind of bring ourselves back to where it should be. See, it's an interesting code that has been destroyed by the fact that I'm using the worst possible way of drawing it. But yeah, thanks. I did it. So we can approximate the energy levels in some sort of quantum system here. I want to add one more potential before I pack it up and then go over to the real Saturn so we can test this hardware. So let's just try potential case number 2, where we have a finite well. In which case, if xi is less than, let's call this, we're going from 0 to 10. So if it's less than 2 nanometers, or, is this or? Xi greater than 8 nanometers, then Vi should be 1 electron volt, else it will be 0. And this will be case 2. This is finite well. Fine. Whoa, okay. So, we need to figure out what the actual energy... And the well is skiddier now, so the energy should be higher. So, let's try going up a couple volt, if it will... You know what occurs to me? That the drop function is super slow, but it only needs to happen once. So instead of having it happen on my draw every time, we could just call it every time we update the graph. So let me do that. You no longer need the callback for my draw, we just need to call it when we need it. When do we want to use it? We'll just call it anytime I change a value. This is still a little bit redundant, but it'll do the job. And definitely when this happens. That way we're allowed to have dead frames. Huh. Well, it definitely works a lot smoother. I just don't get why there's the boundaries, so I'm looking. Try seeing if this thing gets wider. Okay. Start out with a my draw. Okay, what am I doing here? Okay, so what I wanted was... Am I changing here? Well, I guess it kind of... Everything's kind of fine where it is. Let's try... Oh, that's what I wanted to do. I wanted to take away that y squared on the chute. That way we can track the positive and negative change and figure out where everything needs. So... Go. That's disabled. And the second thing was, let's make the finite well a little bit lighter. Try and match what we're going for. Potential here. For this, we'll do 0.5F and 9.5F. It's a 9 micron well, or 9 nanometer well, as opposed to what was it, like a 6 nanometer well. I don't know what the green bands came from. Weird to me. Okay, there we go. So this is our finite well. And now we're going to try and search for the right energy. Come on. 7? We're waiting for that sign on the edge to flip. There we go. Getting closer. This close. I think this is about here. So now this is the energy level for the finite well, which is slightly skinnier than the infinite well that we set up, but you know, whatever. I guess now we can input things without having to wait for the draw command constantly. Got some weird green bars on the edge of the screen, but I don't know what that's about. So I think the last step is to copy a tiled version of this guy onto the real Saturn and play it on the real Saturn. So let me go ahead and get out of here. And we'll see. Let's see, what do I need? The ISO, the Q, and the bin. I guess I only really need 2 out of those 3 things. I could use the ISO or I can use the Q and the bin. Let's do quantum. Check that. And then we'll go back over to Saturn view. So let's see, is that on right now? Okay, Hoppage, wake up. Waking up? There it is, okay. Start up the real Saturn. Oh, come on. Gotta restart the system. Sometimes the sadiator for some reason doesn't see it. When I swap the cards, I'm in a little bit of trouble. Occasionally. Usually. Starting up for real now? There we go. I should probably switch to the actual display because I'm looking at the delayed feed. I should be looking at the live feed. My live feed. There it is. Okay, so now on real live hardware, we're going to do the quantum mechanics simulation on the Sega Saturn. Press start. There we go. Alright, so this is our infinite well. Okay, so I'm not going to go back and search for that yet. I'm going to do finite well. I'm going to marginally increase the energy level. Wow, this actually feels... This controls so much better on the Saturn than it does on the emulator. For some reason, I can't get that out. There we go. So now we can manually search for energy levels on our quantum well. And figure out where they should be. Based off, we kind of have to eyeball it though. That looks. So we have a quantum well simulator. There we go. So let's go back and try to find our high order mode. on a high order mode optics like here, but no, crap, no. I'm surprised about how well this is behaving on the Saturn as opposed to the emulator. Okay, so this times 1.5 would be basically somewhere around probably 120. Yeah, it's a little bit of a different situation when you're talking about having a proper simulation tower compared to a 20-year-old piece of hardware designed for video. See you getting closer. Oh, almost. Almost. There we go. Getting there. Almost. Yeah, that's close enough. It's going to be really hard in the simple harmonic oscillator, probably because I made the potential a little bit too steep or narrow. I don't know. I don't know. So something I could probably make it easier to convert on energies. But that's roughly where I expected that second energy level to be, and there it is. You can keep going and try to find the third, fourth, and whatever. I think I'm going to push this to GitHub after the stream is done. You see it running on a real Saturn. If you want to, you can run it on your own. You can take the code and you can add your own potential wells to it, and hopefully it'll work. But no, that's the quantum well simulator on the Sega Saturn running. I don't know if you guys want to see anything else. I feel like I accomplished what I set out to do tonight, and it's been 3.5 hours or so. It's a good length stream. So if you guys want to see any other potential profiles, you want me to add a feature or something like that, we can keep going for a little bit. Otherwise, I think I'm going to close up shop for the night. Did what I set out to do. Okay, I take the silence as everyone's satisfied with tonight's results. So I'm going to go ahead... Oh, thanks, Razor. So I'm going to go ahead and I'm going to, package the code and probably push it to GitHub or something, and it'll be attached to the video when it gets pushed over to YouTube. You guys can play around with it too. Should work on pseudo Saturn Kai and whatever. Actually, let me just check real quick the make file. Let's go back to on screen. So, there is a flag for pseudo Saturn Kai somewhere in here. Let me go over back to Forsaken Plane. And it's not included by default, but it probably should be. There we go. Saturn Kai support. There we go. Now it should work on pseudo Saturn Kai. So let me go ahead and rebuild. Wait. There we go. I don't follow. Wait. Robin? I'm not familiar with the raw bin for. Here's what I have. When I build an ISO over here, and then a queue and a bin. And if you know how to build to whatever format you want, you can just take the... Oh wait, this is wrong. Here. Yeah. So I have the bin, queue, and the ISO, and I don't ever use the conf. I don't even know what that's for, that or the map. But if you want to take the source code, it's all in main.c in the make file, and you run it yourself, you can compile it for whatever thing that you need. Alright. But otherwise, I feel like this ISO or this bin queue pair by itself will be able to run on whatever you want to run it on. So, I think that's it for the night. I'll be on more frequently once I'm done with this project I have going on at work. I'm working from home right now, because of the pandemic and whatnot. Once I'm done with this simulation thing I've got to do here for my own work, I'll be making much more frequent appearances on Twitch, doing Saturn programming stuff. My next thing on the docket is helping Pona with a Great Value Engine, hopefully by playing around with Blender and getting a good pipeline set up to use his engine. As always, you guys just go ahead and wait for the YouTube video to come out. I'll attach the GitHub link to that so you can play with this code yourself. Find me on the Sega Extreme Discord and just at me and I'll answer your questions that you want. But otherwise, I think that's it for the night. So if no one else has anything to add to the code, I'll go ahead and see you guys next time, whenever that is.